Okay, we're going to finish up the last little bit of chapter 10, and then we'll roll into 11. Seems like a good chapter after that. So in chapter 10, we've talked about acids and bases, and we talked about obviously a bunch of stuff. We talked about, again, Kw, which is the concentration of H plus times concentration of OH minus. And that equals 1 times 10 to the minus 14. Remember, we can basically use this if we have either the H plus or OH minus concentration. Again, a reminder, H plus, H3O plus, basically same thing. And here, it's really the same calculation regardless of which one you have. You're basically just going to take the Kw value, which is 1 times 10 to the minus 14, and you're going to divide it by the other concentration. And again, obviously, if you're doing OH minus, exact same calculation. So one of the nice things about sort of these calculations in this chapter is they are kind of like the same calculation for different things, but you basically do the exact same calculation. We can obviously compare our acid part really of our solution to our base part of our solution, and we can determine whether or not it is going to be acidic, basic, or neutral by which one is larger. If your H plus concentration is larger than your OH minus, then you have an acidic solution. If your OH minus, which is the base part of the solution, is larger than the H plus, then you have a basic solution. And if they do equal each other, you do have a neutral solution in that case. We also talked about and by the way, the relationship between H plus and OH minus is sort of a opposite relationship. As one goes up, the other goes down, and vice versa. So again, if the H plus concentration increases, then the OH minus comes down. And if the OH minus concentration increases, the H plus concentration comes down. So they do run basically opposites of each other. And again, as one goes up, the other basically comes down. We talked about the pH scale, which runs from 0 to 7 to 14. Again, less than 7 is acidic. Above 7 is basic, and 7 is neutral. 7 is sort of like your center point. As you head towards 14, it becomes more basic. And if you head towards 0, it becomes more acidic. You can calculate the pH by taking the pH is equal to minus the log of the H plus concentration. Remember that as we talked about with your calculators, depending on sort of what type of calculator you got going on for yourself, as to how you would want to punch it in. Again, if you have more of a display calculator, which actually shows log when you hit log, you basically punch this one in, and all the other sort of formulas exactly the way it's written. You would do your negative button, you would hit your log button, and then you would put your number in, probably with your exponent button as well. If you have a non-display calculator, which again is usually calculators where you just hit the log button and it says error, you actually have to go backwards with this calculation and pretty much all the other ones. So if you had a non-display calculator, you would put the number in probably with your exponent. You would then hit the log button and then hit the negative button. So pretty much as we talked about, kind of going in this direction, display calculators, non-display always has to kind of work the back way, or from the back right to left, basically. We also saw that there is a different sort of calculation that we could do that doesn't measure the H plus concentration, but actually measures the OH minus concentration, and that's known as the POH. And again, each of these names actually tells you what you need to calculate it. So pH means you need the H plus concentration or the H3O plus concentration. POH means you need the OH minus. Thank you. Concentration. It's minus the log here of the OH minus concentration. Now, there's a really nice relationship between those two. If you take the pH plus the POH, it does equal 14, which means that in certain situations, if you have the OH minus concentration, you could calculate the pOH and then just subtract 14 and you'll have the pH pretty quickly. So it's a good way to do that. So as we talked about last time, it does give you a few different options as to how you could do these problems. Again, you could use KW in certain cases. You might not have to even use KW. So you could use some of those relationships. We also saw that if you actually do have the pH given to you, directly from that number, you could actually calculate the H plus concentration, and that is the inverse log of the negative pH. Once again, when you do that on your calculator, on most people's calculator, when they hit the inverse log, it oftentimes will pop up like a 10 and a caret, and you could go negative the pH. Again, to punch the inverse log into your calculator, most people's calculators, you got to go upper left corner and hit the second button or the shift button, and then hit the log button, and then obviously make negative in your pH value. Again, if you have a non-display calculator, you also need to work backwards on this formula as well. So if you have a non-display calculator, you would need to put the pH in first, then make it negative, and then hit second log. So again, same idea, display forward in the formula, non-display backwards. Similarly here, if we have the pOH, we can get directly from that the OH minus concentration, and that would be the inverse log of the minus pOH. And again, that's going to most likely put a 10 and a caret minus pOH. Remember that when you are asked the question of, is the solution acidic, basic, or neutral, there's just one answer to that question, and don't give multiple answers to that question. Again, very commonly, as I mentioned before, people will calculate the pH and go, it's above 7, so it's like basic, and then do this guy and go, it's below 7, it's acidic, and it's the same solution, so it can't be both things. So 100% of the time, I would always look at the pH value, as that is most likely the scale that you have in your head and you're thinking about. Remember that the pOH scale actually runs opposite. So if you have a high pH, you'll have a low pOH, and if you have a low pH, you'll have a high pOH. So they do run opposite. Yeah. Yeah, so again, H plus, H3O plus is interchangeable. So wherever, I put H plus, that's the same thing as H3O plus. These are all basically H3O plus. It's just another way that you can look at sort of the acid part of it. So it's all the same thing. It's interchangeable for sure. Yeah, it means the same thing. The reason again why you sometimes will see H plus versus H3O plus is a lot of times people will write the reaction and have water involved in the reaction. And because of the Bronsted-Lowry definition, because water technically is involved always with an acid, it's able to basically, when it goes for a swim, donate the H plus to the H2O, and that's how you make basically H3O plus. You can also very commonly write the acid just dissolving in water without the water present, and you would just break the acid like HCl into H plus and Cl minus. So again, they're interchangeable, and anywhere both in sort of formulas and even really in equations as well, anywhere there's an H plus, it's the same thing as H3O plus. It basically means the acid part. Other questions? All right, so at the end there, we were talking about buffers, and just one more time on buffers here, just to make sure that is a highlighter here. So a reminder that a buffer is a solution that can resist changes in pH when you add more acid or base to it. Also a reminder that, as I mentioned last time, sometimes people have a misunderstanding about buffers and always think that they has to be a neutral solution. And again, they do not. They could definitely be a neutral solution. But again, you can make really a buffer at any pH you like along the pH scale. You could have acidic buffers, you could have basic buffers, and you could also have neutral buffer as well. But basically what it means if you do have a buffer is whatever pH it basically starts at, it basically will be able to sort of maintain that pH. You won't see a big change in pH either up or down when you add additional acid or base to it. And the reason it's really able to do that, as we talked about at the end last time, is it's made up of one of two combinations, either a weak acid and the salt of its conjugate base, or it's made up of a weak base and the salt of its conjugate acid. And again, really, these things are still the basic Bronsted-Lowry definition. They are basically just a difference of 1H plus, the acid conjugate base pairs basically here. You cannot, as I talked about last time, have a buffer that's actually made up of a strong acid or strong base. And the reason for that is, in order for a buffer to work properly, you have to have both parts of the buffer actually in the solution to begin with. And because these are weak acids and weak bases, they are essentially weak electrolytes. Which means if we took something like acetic acid, which is a weak acid, and we take something like sodium acetate, which is a conjugate base. And again, the sodium acetate is really a salt. It's made up of two things. It's made up of a sodium ion and it's made up of a acetate ion. And it really is the acetate ion here that is really the buffer part of it. The sodium is really not doing anything there. It's just hanging out and going for a swim. But really what the buffer is basically these two guys here together. And if you look at those two guys, it is again that Bronsted-Lowry definition of acid and conjugate base. The difference is just 1H plus difference. And again, that is really what you need. This is obviously the acid, and this is the base part of the buffer. So there's a base part of the buffer and there's an acid part of the buffer. And when you put that buffer into a beaker, because really acetic acid is a weak electrolyte, it will set up that equilibrium. If you remember when we talked about weak electrolytes, they had those two arrows that had the reversible reaction. They even put the arrows in the beaker, probably not. And it'll break apart into H plus and acetate. So what happens when you make a buffer like this, for example, is you'll put some acetic acid in there. And then what you'll do is you'll actually put some sodium acetate in there with it. And by putting the sodium acetate in there, what that does is it makes this concentration of the acetate part pretty good. And obviously by adding the acetic acid, you now will have floating around in that solution both of those things. And again, this is what's going to make this a buffer. You have this acid part and you have this base part to your buffer. And that's essential for really how the buffer is able to basically keep the pH from going crazy. As we talked about last time, if you took water, which is not a buffer, and you added either hydrochloric acid to water, you would have hydrochloric acid. It will, because it's a strong acid, strong electrolyte, 100% break apart into H plus and Cl minus. Also, if you added to water sodium hydroxide, it also will 100% break apart into sodium ions and hydroxide ions. So if you looked at, for example, the here, you looked at the beaker for each of those, if you had water and you added these things to it, basically what's going to happen is when you take your water here and you put that HCl in, 100% going to break apart. As I mentioned last time, you're just going to produce a lot of free H plus basically in that. And that amount of free H plus that's floating around means that the concentration of H plus is going to go up a lot because you just basically dumped a bunch of H plus into that water, which is not a buffer. And that's going to cause a pretty big drop in your pH, right? So as the H plus concentration goes up, that means it's more acidic. More acidic means the pH actually goes down closer to 0, becomes more acidic in that case. Same thing would happen if you took your water here and you added the sodium hydroxide to it. It also will 100% break apart. It will produce a bunch of hydroxide ions and also sodium ions. But it is the hydroxide ions that are now going to really increase very quickly in that water solution. So you're going to see the concentration of OH minus jump up a lot. And because OH minus and H plus are tied to each other, as the OH minus concentration goes up, the H plus concentration will drop pretty drastically as well. So we will actually see a drop in the H plus concentration. The result of that is more OH minus than H plus. You'll see the pH really jump pretty high in that case. So again, if you started with water, say at a pH of 7, you got nice neutral water, and you add some HCl to it, maybe it goes from a pH of 7 down to like a pH of 2, a pretty big drop in the pH. Or if you started with that water that's at a pH of 7 and you added some hydroxide, sodium hydroxide to it, may go from 7 to like a pH of 13, a really big swing in pH because it has no way, water, for example, which is not a buffer or any non-buffer solution, it has no way to adjust for all this influx of H plus that's coming in, all this influx of OH minus that's coming in. So it can't handle it. All it could do is just let it float around freely. And because those guys are going to be able to float around freely, you're going to see this really big change in the pH. Now, that is very different than what we have like in a buffer solution, like we have over here on the right. And get rid of some of this here so you can see it. Now, if we took that same hydrochloric acid and added this to our buffer here, we are going to get a little something different that's going to happen than what happened with water, which is not a buffer. So if we took that HCl and we dumped it in here, again, that's basically H plus and Cl minus. What's going to happen when you add the HCl is it's actually going to react with the base part of the buffer. You added an acid, it reacts with the base because those reactions are called acid-base reactions, right? They're not called acid-acid reactions or base-base reactions. So when you add an acid, because this buffer has the base part hanging around in the solution, you will actually get a reaction that will occur between the hydrochloric acid and the sodium acetate, which again is part of that buffer to begin with. It's going to actually be a double displacement reaction, positive, negative, positive, negative. We're going to switch partners here. And you will make, again, acetic acid. And you'll make some sodium chloride. Now, sodium chloride is actually a neutral salt. It won't do anything. It's just going to float around. It's actually going to float around. Sodium ions and chloride ions floating around, really not doing anything to affect the pH. What we also made, which is always what happens with a buffer, is we actually will make the other part of the buffer as a result of this reaction. So we're going to use up a little bit of the base part of the buffer, but we will make a little bit more of the acid part of the buffer, right? So we kind of use a little up, but make a little of the other part of the buffer. So what ends up happening is, as you can see here in this equation, there's no free H plus, because when that H plus comes in, it's going to react with the acetate and it's going to make more acetic acid. So it's going to prevent the formation of free H plus in that solution. And that is what affects the pH a lot, is right. The pH is negative log of the H plus concentration. So if you're able to prevent the H plus ions from building up, which a buffer can do, what that's going to do is essentially leave this guy right here pretty much the same as we started with. We had a little H plus in there to begin with, and whatever that concentration is going to be, this guy is going to be able to be constant, essentially. And because we have essentially the H plus stays relatively constant, so will the pH, will stay relatively constant. So why do I say relatively constant? Because the truth is, if you stick a pH meter in there and you add acid to it, the pH will go down a little bit, but it will not go down drastically. So again, if you start out at pH of 7, maybe it goes down to like 6.9 or something like that, but it's not going to go from like 7 all the way down to 2. You will get a little bit of H plus coming in there, but not a drastic amount of H plus that's going to cause that really big switch in or change in pH. Any questions on that there? Now, if we take this same buffer and steal my picture, I think. Get rid of my HCl. Get rid of that, maybe. There we go. And if we add now sodium hydroxide to this buffer, this again is a source of Na plus and OH minus. And what's going to happen is when you add that, we are going to get a reaction with actually the acid part of the buffer, right? I added sodium hydroxide, which is a base. So now we have the acid part of the buffer in there, and they are going to react. So when they react, we will get the sodium hydroxide reacting with the acetic acid, which is the acid part of the buffer. Also, still a double displacement reaction happening. We're going to switch partners. And in this case, we will once again make the other part of the buffer, which is sodium acetate, will be made. We will also make water in this case. Again, the OH from the base and the H plus from the acid will make water. And obviously, water is not going to affect the pH. This sodium acetate, once again, in this case, we used up a little bit of the acid part of the buffer, but made more of the base part of the buffer. So that's not going to affect the pH. So really, in this case, we're going to basically make more of this guy. And once again, we are not injecting any more H plus into the solution. We're not injecting any free, there's no free OH minus happening in this solution, which means that the concentration of OH minus stays relatively constant. And again, because OH minus and H plus are tied to each other, if the OH minus concentration doesn't change, then basically our H plus concentration will remain relatively constant, and thus our pH will also stay relatively constant as well. Again, if you did add some sodium hydroxide to this buffer, by the way, this buffer starts at a pH of 4.74, and if you added some base to it, it would go up a little bit. Maybe it goes up, like I said, maybe 4.8 something, 4.9, depending on how much you add. But again, it will not go from like 4.74 all the way up to like 10 or 11 or anything like that. And this is how a buffer is able to basically work. A buffer is able to work because you have both an acid part for the buffer and a base part of the buffer. They're both in the solution to begin with. And that allows them, when you add additional acid or base to it, to prevent any formation of a bunch of H plus or a bunch of OH minus in that solution. And what that ultimately does is keep pretty much your H plus concentration constant. And that's how it keeps basically the pH relatively constant. Any questions on that there? So visually, this is sort of, if you were going to make a buffer, for example, you a lot of times will try to have almost equal parts of the acid part of your buffer and the base part of your buffer. And that is because if you add, like we saw there, more acid, like HCl, what's going to happen is that acid is going to react with the base part. And you will generate, dramatically drawn here, more of the acid part, but you'll use up some of the base part here. And same thing will happen if you add more base, like sodium hydroxide. It will react with the acid part of the buffer, and it will use up some of that, but it will generate the base part of the buffer and use up some of the acid part. So in a sense, a buffer is almost regenerating half of the buffer every time you add acid or base to it, but it is using up the other. That's also why there is what's known as buffer capacity. There's a limit to how good a buffer could be. If I grab like the acid, right, and I just keep adding acid, what's going to keep happening? Every time I add acid, I'm going to chew up some of the base part, right? And if I keep adding, at some point, there will be no more base part to handle the acid. And if I continue to add that, at that point, you will be just dropping in a bunch of H plus, and you will at that point see a pretty big jump in the pH. Also, if you don't make your buffer correctly in terms of the molarity of it, and you grab hypothetically like the 18 molar HCl rather than the 0.1 molar HCl, and you added that to your buffer, you'll blow right through it because it cannot handle it. So when you actually make a buffer, you want to think about the concentration of the acid and base you might be adding to it, and you want to make it appropriate to handle whatever may be coming in. Otherwise, it is possible to kind of blow through a buffer if you add too much or too strong of an acid or base to it. Any questions on buffers or how they work? Yeah. Okay. All right, then the last thing we're going to talk about in this chapter is Le Chatelier's principle. And Le Chatelier's principle is based off of a certain type of reaction, which is this type of reaction, and this is a reversible reaction, similar to what we saw with a weak electrolyte. So if we have this reaction, this is a reversible reaction. And what that again means is it has a forward direction, which means it's going from reactants to products. In these type of reactions, what will happen is at some point, you'll make enough products that the products will decide we're going to react and head back the other way. So at some point, you'll build up enough products, and the products will head back the other way towards the reactant side, and that's what's known as a reverse reaction. And this will continue until basically the rate of the forward direction will equal the rate of the reverse direction. And that is what is actually known as chemical equilibrium. Now, sometimes people think equilibrium means equal, like you got equal amounts on both sides. And it doesn't mean that in this case. It means it's actually talking about how fast it's going one way and how fast it's going the other way. And they're going to end up going in both directions at the exact same rate. What that will essentially do is not necessarily mean you have equal amounts of reactants and products, but what it means is wherever those guys are in terms of their concentration, in terms of their pressure, when it reaches equilibrium, they're just going to be locked in. They can't change. They won't change because just as quick as they lose a little, it comes right back. They lose a little, it comes right back because they're going back and forth at the exact same rate. So, for example, if this thing reached equilibrium, let's just say it had 2 molar this guy, 4 molar this guy, 1 molar this guy, and I'll go 2 molar of that guy. What that means is those guys will be able to just keep at those concentrations endlessly. It's just going to keep going back and forth at the same rate, unless you do something to it to screw it up, which is basically what we're going to talk about in a second. So you can actually do something to it to mess up the equilibrium, mess up that rate of it going back and forth at the same sort of rate, and it will really want to always get back to equilibrium. So no matter even if you screw it up, these type of reactions always know I just need to get back myself to that equal rate of forward and reverse direction. So it will actually self-correct itself multiple times, even if you screw around with it and mess it up. It's able to almost self-correct itself, and that's really what Le Chatelier's principle we're going to talk about here in a second is basically about. There is also a relationship that you can get from an equilibrium reaction, and it's actually known as capital K, and this is what is known as the equilibrium constant. And equilibrium constants are for these type of reactions, and you can actually calculate the equilibrium constant by taking the products to their coefficients over the reactants to its coefficients. So the nice thing about K is if you calculate it, you need the equilibrium concentrations of everybody, which is typically molarity. And it's actually just a number. There's usually no units associated with it. It's just a number. And what that number tells you is basically here we're taking the concentration of our products over our reactants. And if you have a large value of K, what that means is it will tell you that when you reach equilibrium, you should mainly have products or reactants. If I have a large value of K, what do you think? Just mathematically speaking. If it's basically products divided by reactants, how do you get a large number? Which one has to be bigger, top or bottom? Top number. So if you have a large value of K, that means that when you reach equilibrium, you basically will have mainly products present. So you'll mainly have products present. And if you have a small value of K, that means that in that case, the bottom guy has to be a larger number, top guy has to be a smaller number. You will actually mainly have reactants. So we can calculate the equilibrium constant, sometimes called Kc, Kp. There's all kinds of K values. The only thing that you do not include, by the way, in these expressions, you do not include anything that's a solid or a liquid. So if you have an equation and there's a solid or liquid, they do not go into the equilibrium expression. That pretty much leaves you only two things that go in. That is anything that's aqueous and anything that's a gas. So those two things get included if you have a solid or liquid. They actually don't participate in the equilibrium. So if you think about a solid, like a rock, it's just sitting there, right? It's not like you're doing much. And that's the same idea here. It's not going to participate in the equilibrium, which is mainly a solution, things floating around. And if you have a pure liquid like water, its concentration is pretty high and it doesn't really change all that much in a reaction. So it stays relatively constant. So those are two things we don't include, solid liquids, but aqueous and gas is included. You know, if you had something like N2 plus H2, hey, no parentheses on that there. Yeah. H2, which is a gas, and you get NH3, which is a gas. Do a little balancing, a 2 there, and I think a 3 there. We could write the equilibrium expression for this, and it would be the Kc equals the concentration of NH3 at equilibrium, and we do need to square it because of the coefficient, so it would be squared divided by the concentration of N2, coefficient is 1, which means we don't really need to put the 1 on top, times the concentration of H2, which does need to be cubed because of the coefficient. And that would be the equilibrium expression. If I had the equilibrium concentrations of all these guys, I pop it in there, I get a number, and it'll tell me something. Now, these are all also gases, so they all get included. Just to show you, there's a lot of different K-type values. There's actually one you could write. When we think about gases, we think about pressures, right? So you could write a similar expression of the partial pressure squared of NH3 divided by the partial pressure of N2, partial pressure cubed of H2. So Kc, C stands for concentration. So you would do that with concentrations like molarities and stuff like that. Kp is like pressures. You could do the same relationship with pressures. And again, you would use something like atmospheres for everybody at equilibrium would be pressures. We've actually seen an equilibrium expression. We actually used it earlier on in this chapter. That was our friend Kw. Kw is based off of water. That is an equilibrium reaction. And surprisingly enough, we take our products, which is H plus times OH minus, and we divide it by our reactant. Should I include water? It is a liquid, right? It is not included. That's why when we did KW, there is no water on the bottom there. It is just the concentration of H plus times concentration of OH minus, and that was the one that equaled the 1 times 10 to minus 14. That's actually an equilibrium expression and an equilibrium constant, which is what KW is. Now, one idea of equilibrium that sometimes confuses people is this: equilibrium is continuously happening. So the reactions going to the products going back to the reactants. It is continuously happening, even though you may look at like your beaker and it may look like it's done. There's nothing else happening. You know, you just look at it, maybe it turned red and it's just red at this point, or orange, and it doesn't look like anything's happening. But if you were to like super zoom in, you would see reactants going to products going to reactants, constantly happening, going back and forth. So there is a lot of activity that happens a lot, even though if you look at it on the big scale, it doesn't look like anything's happening, it's over. But it's constantly having those reactions going in both directions. And that's what keeps it. For example, if you have like an orange solution, that's what keeps it orange. Basically, it's that constant back and forth that prevents it from continuing one way or the other. When we have an equilibrium constant, it is specific for the reaction as it's written, and it's also specific for the temperature. The temperature is the only thing that could affect the value of the equilibrium constant. That's why sometimes you'll see when we use this thing here earlier, a lot of the problems said like at 25 degrees, because at 25 degrees, KW is 1 times 10 to minus 14. If you did it at like 5 degrees, the KW value is different than that number. So if you change the temperature, the value of the equilibrium expression will actually change. Any questions on that there? Okay, so we have these guys that are at equilibrium, and Le Chatelier's principle is basically this idea where you have a reaction that's at equilibrium. And as I mentioned before, frankly, you do something to it that screws it up, basically. A nicer way of saying that, I suppose, is you add a stress to your system that's at equilibrium. So again, we have this reaction that's going back and forth at the exact same rate. Everybody's nice and happy, and then you do something to it. So there are a few things that are considered stresses. You could change the concentration. You can change the pressure or volume. You could change the temperature, or you could add a catalyst. So these are basically 4 things that you could do to a system that's at equilibrium that will essentially, in most of the cases, mess it up. And as I mentioned before, these type of reactions, pretty much even if you mess them up, they will self-correct themselves to get back to equilibrium. So you can mess it up for a bit, and then it's going to figure out how to get back to that equilibrium. How it's able to get back to equilibrium pretty much means you have 3 options usually. It will either shift to the right, which means it's going to go towards the products. So you need to make some more products to get back to equilibrium. It will shift to the left, which means you need to actually make more reactants when you look at the equation. And there's actually some stuff that even though you did something to it, will actually cause no change. Even though you kind of did something to it, it won't cause any type of change that will occur. All right, so we're going to take a look at each of these and sort of what happens when we kind of change these guys. So the first thing we're going to look at for Le Chatelier's principle is concentration. And basically, there's 2 things you could do with concentration. You could either add more or you could remove. Basically, those are your 2 options. If you add more concentration, it will shift away from the side you added it to. And when we're talking about side, we're actually talking about the equation, like reactant side, product side of the arrow is basically what we're talking about. So way to remember that is AA, add away, is basically what will happen. So if you add products, it will cause the reaction to shift to the left and make more reactants. If you add reactants, it will cause it to shift to the right and make more products. Now, if you remove something, it will shift towards the side you removed. So if we look at this, for example, and we have a wonderfully drawn stick figure. It is advanced stick figures. They have faces. That's what I took after basic stick figures there. Sure got that. So I got them on like a seesaw here. This guy on the left is our reactants. This guy on the right is our products. And we're at equilibrium at this point. Right? So let's say we added more products, right? So we threw some people there on the product side. It's going to cause this effect. Right. Now to fix this, I need more people on the right-hand side or left-hand side? Left. We add it to the right, it shifts away to the left to balance it out, if you want to think about it that way. And now we will once again get ourselves back to equilibrium. And again, we're back to equilibrium. Now, again, same deal here. If we take our guys here, and again, we have reactants, we have products, and again, we'll say we're at equilibrium. Let's say we remove some products. So this guy decides, I'm good, I'm just gonna hop off. So he hops off. This is what's gonna happen, right? This poor guy over here is gonna come crashing down, probably not so happy. In this case, I need more people on the left or right. Yeah, so we remove from the right, it's gonna go towards the side we removed it from to fix it. Like there's a hole over there, so we got to fill it with something. So it's going to bring this back to equilibrium at this point. Any questions on that? Again, back to equilibrium. Yeah. So how do we add more concentration? Pretty simple. You pick up the reagent bottle and you just dump it into the beaker, basically. If you need to remove something, you can't just reach in and grab ions that are floating around. Never a good idea to reach in with your hand into a solution. But what we can do is add something that will make a solid, right? Which is not part of the equilibrium. So that's like going in there and taking something out. We also can make water, which is sometimes hard to see, but you could actually make water if you had H plus floating around or OH minus floating around, and that would make water, which is a pure liquid. That would be like removing H plus or OH minus. So let's talk a little bit about pressure and volume next. Pressure and volume are usually tied together, and it is related to, if you remember our gas chapter there, I think was our friend Boyle. He did pressure volume relationship. And as pressure went up, the volume went down, right? And as pressure went down, the volume went up, right? So in a case with Le Chatelier's principle, if the pressure goes up, the volume goes down. So what happens in this case is we have a smaller volume. We have all these gas molecules in there. And because they're in a smaller volume, there's going to be a lot more collisions. So that's why we see the pressure start to spike up because we lowered the volume. What we want to do is sort of counteract that. So we want to have to bring the pressure back down. So because the volume is small, we would actually need to go to the side, or it will shift to the side with the least number of gas molecules. So because basically the volume slams small, in that smaller volume, you need less gas molecules to kind of keep the pressure from going way crazily up. Vice versa here, if we drop the pressure, the volume went up, we now have this big volume with gas molecules flying around. So because there's a lot more room for them to fly around in, there's going to be less collisions. We're going to see the pressure start to drop. So what we want to do is kind of bring the pressure back up. So in this case where we have a larger volume, we actually need to shift to the side with more gas molecules. And that obviously, both of those are dependent on the actual equation. to figure out which side has more or less gas molecules, you don't want to overcomplicate it. Just look at everyone that has a G and look at the coefficients and add them up on each side. And whichever one has more things with G as gas state, and look at the coefficients will tell you that. So if we take that one we just looked up there, N2, right, plus some 3H2 and a little NH3. So tell me what's going to happen for each of these. Will it shift to the left? Will it shift to the right? Will there be no change? If I do the following, let's see, let's add more H2. If I remove NH3, if I increase the pressure, if I increase the volume. So for each of those, what should happen? Should it go to the right? Okay, so let's take a look. We're going to add some H2. So really, we just want to think about where H2 is. H2 is over here on the left-hand side. So we're adding more reactants. When we add, it goes away, which means it should shift to the right in this case. We added more reactants, we should make more products. The reason we're going to really make more products is when we add more reactants, there's a lot more reactants to find each other, right? They're going to be able to find each other a lot faster. And that's going to cause the forward reaction to occur going to the right-hand side. So that's basically away from the side that we added it to. Any questions on that there? Now, if we look at removing NH3, NH3 is on the right-hand side. When we remove something, it comes towards the side we removed, right? When the guy jumped off the little seesaw, right? It went towards the side he jumped off of. So in this case, this will also cause the reaction to go to the right in this case. You can think of it one of two ways, like you created a hole over there on the right-hand side, so you got to go fill the hole basically because you removed it. What's really happening in this case is actually the same thing. We now have less products. We have a lot more reactants. So a lot more reactants are going to be able to react, and the forward reaction is actually going to take place in this particular case. Now I'm going to increase the pressure. That means that really my volume is going to go down. I personally always think about this one in terms of volume. That means I have a small volume. Do I need more or less gas molecules in a smaller place? I need less. So we want to go to the equation, find everybody that has a G. That is one gas molecule there. That is 3 gas molecules. That's basically just the coefficients. That's a grand total of 4 gas molecules on the left-hand side. Right-hand side, we got just this guy, which is 2 gas molecules. So in this case, it's actually going to shift to the right as well. I picked all right so far. That's not bad. Any questions on that one? So obviously this one would be opposite. We have a larger volume, which means that our pressure is going to come down. But again, if we think about the volume and that larger volume, we need more gas molecules. And if we look at it as we just did there, the left-hand side there actually has more gas molecules. Any questions on any of those there? So we've talked about shifting to the left, shifting to the right. That's in relationship, obviously, to the balance equation. And basically what's happening in each of those cases is either you're going to cause the forward reaction to occur or you're going to cause the reverse reaction basically to occur based on the availability really of your reactants or products as present. Any question on pressure, volume, concentration? The last major thing that sort of affects Le Chatelier's principle in these type of reactions is temperature. And temperature works the same way as concentration. So if you increase the temperature, it will shift away. And if you decrease the temperature, it will shift towards it. So the important part of this one is, how do you know where temperature is in the equation? So the reaction will be one of two things. It will be either a exothermic reaction. And exothermic reactions means that energy is released. So when we think about exothermic reactions, we think of heat and energy and temperature, if you will, as being a product. So when we have a reaction that's exothermic, we think of heat, energy, all that stuff as being a product, which means if we have an exothermic reaction and increase the temperature, it should shift to the left. If we have an exothermic reaction, decrease the temperature, it should go towards the heat and shift to the right in this case. The exothermic is oftentimes given to you with the delta H value. That is what is known as the change in enthalpy. It is basically a energy value. And most of the time, or a lot of the times, they will just give you the equation, and next to it, it'll go delta H is negative, whatever number it is. And these values are typically negative. It doesn't really matter the number, but if you see a delta H and the value is negative, that tells you that it's an exothermic reaction. That's very commonly how it's sort of displayed in equations. Now, if you have an endothermic reaction, it's sort of the opposite. It is energy is absorbed. And we think of it as being a reactant in that case, on the left-hand side, basically. So we think of it as being a reactant. And that means if you have an endothermic reaction, heat and energy, if you add heat or increase the temperature, it will shift to the right away from the left-hand side. If you decrease the temperature, like throw all your test tubes on ice, it will come to the left there as it's being removed. Also, delta H for endothermic is typically a positive number. So if you see a positive number, again, the number really doesn't matter. It's just really, is it negative or positive? Question on temperature. So you have to determine, is it exothermic or endothermic? And then again, basically it works like concentration. If you increase temperature, it goes away. If you decrease it, it goes towards whichever side has the heat or energy associated with it. Any questions on that there? The last sort of effect is a catalyst, and it will actually have no change. A catalyst is, as we talked about, I think previously, is not a reactant. It's not a product. It's just there really to speed up the reaction, so it'll reach equilibrium a lot quicker, but it'll have no effect on it. Other things that could have no effect on a reaction is if you have like a noble gas, they're chemically inert, so they usually will not have too much of an effect. Also, another way you could get a no change is actually with the pressure volume. So if you have an equation where you have equal number of moles on both sides, there is no greater side or less side of moles of gases. So it's a tie. In that case, it's a no change. So that's really the three ways that you could kind of get a no change. You add a catalyst, maybe a noble gas, and in the gases, when you compare them, there's the same number of gas molecules on each side of the equation. Any questions on that there? So putting these all together, let's take a look at one more here. We got like this plus this makes this. And we'll do this, right? All right, so same deal. Will it shift to the left, shift to the right, or no change? If I do the following, let me see here. Let's say we remove F3, Fe. We add FeSCN2 plus. We increase the temperature. We add SCN minus, and then we decrease the temperature. All right, so let's take a look. In this first one, we're going to remove Fe. So Fe is over here. When we remove something, it comes towards it. So it should cause the equilibrium to shift to the left. Again, you can think of it like you made a hole on that side. It's got to go fill it, right? So it's going to go that way to kind of fill the hole. What's really happening is you now have more products and reactants, so it's going to cause the reverse reaction to actually occur and head that direction. If we add some of our FeSCN2 plus, that is over here on the right-hand side. So when we add away, right, AA, so that's going to also cause this guy to go to the left, away from the side we added it to. Again, same reasoning, really. We now have more products than reactants, so it's going to cause the reverse reaction basically to occur, and that's why it's really going away from it. This reaction is endothermic or exothermic? It is exothermic. Our heat is over here, right? So that is exothermic. So in this case, when we increase the temperature, it would be like adding more products, which is going to cause it to go away from the side we added it to. So it will cause it to shift to the left. Question on that one there. If we add some SCN minus, that's right there on the left-hand side. Again, we're going to add away. So it's on the left, it's going to go away. So finally, we will shift to the right in this case. Again, what's happening here really is you've added more reactants. More reactants are going to find each other, and that's going to cause the forward reaction to occur, which is why it goes to the right. If we decrease the temperature, that would be like you threw everything on ice. That would be like removing our product over there, which is our heat. Again, that's going to cause a hole over there on the right-hand side. So we got to go fill that hole, and it's going to go towards it to basically fill it. And lastly, if I add a catalyst, it's going to be no change, yeah? Any questions on Le Chatelier's principle? Okay, we're going to continue on here. We are now transitioning to organic chemistry, which means you could slide your calculator away. Not too far because you'll need it for exam 3, but a little bit away, you can slide it. All right, no more calculations from here on out. It's just all, memorization, I guess, or whatever you want to think about. All right, so we're going to talk about organic chemistry here, which is chapter 11. So let us get into it. Let's start with pretty much the first sentence you read in any organic book, which is organic chemistry is really the study of carbon-based compounds. Pretty much organic compounds pretty much have this arrangement. The basis or backbone of all organic molecules are essentially carbons attached to carbons. And attached to those carbons are usually hydrogens. And that really is sort of your basic or basis of most organic compounds. Now, as we will talk about in pretty much all the organic chapters that we cover, along the way, we kind of get rid of maybe some of these hydrogens and replace it with some other elements, which cause other types of organic compounds. But still, the basic sort of backbone, if you will, of any organic molecule is going to be those carbons attached to carbons and mostly hydrogens involved. And again, we do, as I mentioned before, kind of substitute out hydrogen for other elements like oxygens, nitrogens, and so forth, which gives us some different types of organic compounds. As we'll also talk about, and we have talked about previously, clearly if you have a carbon-carbon bond and if you have a carbon-hydrogen bond, both of these bonds are those non-polar bonds. If you remember from our bonding chapter, obviously difference in electronegativity for carbon and carbon is 0. And the difference in electronegativity between hydrogen and carbon, that's 2.5 minus 2.1 gives you 0.4, which is the upper cutoff of non-polar. So that's why also a lot of organic compounds, because of how they are basically made up of these bonds, that's why a lot of them are non-polar for the vast majority of them, or at least I would say have a part of the molecule that definitely is non-polar. As we will also see as we go through the different parts here of organic chemistry in these different chapters, you can definitely have an organic compound where part of it's non-polar, but it does contain a little group that is polar. So you can have sort of both things happening in an organic compound, which makes it somewhat unique in a sense. So an organic compound, as I mentioned, is made up pretty much of our carbons and hydrogens. That also means there is no ionic compound happening here. These are all covalently bonded. These are things that are sharing electrons. And again, as I mentioned, along the way, we will substitute out hydrogen for other elements like oxygen, sulfur, nitrogen, phosphorus. Everybody in group 7, those halogens get into organic a lot. A lot of organic compounds are found in things like gasoline, shampoos, medicine. That's pretty much what gasoline is. It's just a long chain of carbons attached to each other. Octane, right? 91 octane. That's like 8 carbons attached to each other, is basically what that is. They get that, by the way, from breaking up oil, which is even longer stretch of carbons. They do a process sometimes known as cracking. They crack it up into smaller pieces, and you get things like, gasoline and other type of products that come out of it. Now, organic compounds are written with carbon first, usually hydrogen when you write the formulas, and then you add the other elements that may be there. So that's usually the order as how you kind of put the formula together: carbon, hydrogen, and then whatever else may be there if there's other elements involved when you're writing a formula. Now, because organic compounds are typically nonpolar, or at least definitely have a nonpolar part, they have covalent bonds. They have really low melting and boiling points, and that is because for a lot of them are nonpolar compounds. And nonpolar compounds will essentially use what is known as dispersion forces. And dispersion forces, I think we've talked about a little bit along the way, are these very weak intermolecular forces. Intermolecular forces are the forces of how one molecule interacts with another. So that's basically how two molecules interact with each other. Two of the same molecules, two different molecules. Intermolecular forces is basically how they interact. And if they're nonpolar, they're going to use the dispersion forces, which is pretty much your weakest intermolecular force you could have. And because of that, you just sneeze at them and pretty much they'll go into the gas phase. They're not going to hold together very tightly. That's why they have very low melting points and boiling points. A lot of organic compounds are what are known as being volatile, which means even though they're a liquid, because they're held together by these really weak forces, they'll just pop into the gas phase very, very easily. And a lot of little organic compounds or basic organic compounds are gases, like methane that comes out of the gas chute here. Yeah, when you light your Bunsen burner, it's a gas. Methane, propane, butane, right? Those are all things that are gases, right? That we typically use. Also very flammable, right? A lot of those things. And they are very flammable. And organic guys are typically ones that like to go through combustion reactions. So they typically are those guys that if you take an organic compound, you add a little oxygen, those are the ones that we talked about, you get CO2 and water basically produced. So even when you light your Bunsen burner, you're actually making CO2 and water, even though you can't see it. For example, if you turned your Bunsen burner onto the bench top, you would actually see the water because the bench is really cold, they're very hot, condensation will occur, and you actually see the water that's being made that you can't actually see as it's actually happening. Now, because of that, that means that a lot of organic compounds are pretty much not going to be soluble in water. They're not going to mix really well with water because water is a polar molecule. So water is polar. And what water wants to use for an intermolecular force is hydrogen bonding. And hydrogen bonding is a bond between hydrogen and nitrogen, oxygen, and fluorine, basically. So hydrogen bonding is very, very different than dispersion forces. So when those two guys get together, they have no way to keep that interaction going. So I oftentimes just use the example like oil and vinegar salad dressing, right? You can kind of mix it up, right? And it'll stay mixed for a bit. But if you leave the bottle there, right, everybody will separate out from each other because they cannot maintain that interaction over a long period of time. If you ever seen an oil spill, right, in the ocean, where does the oil end up? Up on top floating, right? Because it will not mix, which makes it a little bit easier to clean up because it's not getting all mixed with everything and you can actually get it out. Not too bad. Now, like I said, organic compounds are very different than inorganic compounds. Typically, inorganic compounds are like our ionic compounds, like sodium chloride, metal, non-metal together. Those guys are held together, ionic compounds, by really, really strong forces. They're held together by that electrostatic attraction. Opposites attract, positive, negative attraction. That is like probably one of the strongest attractive forces you can have. And that's why you can take something, for example, like sodium chloride, and you could heat the heck out of it, and it will never go into the gas phase because it's held together very, very tightly. It will actually just start to melt. So inorganic guys, like ionic compounds, they typically will have higher melting points, higher boiling points than your organic compounds, because a lot of those guys are held together by dipole, hydrogen bonding. You know, these guys have a much stronger attractive force. So here's a table from your book of some of the comparisons of organic and inorganic. Again, as we talked about, inorganic mostly metals and nonmetals, organic typically all nonmetals, carbons definitely involved in hydrogen. Typically they're nonpolar organic versus ionic compounds or polar compounds. And again, lower melting points, boiling points in organic, higher there in inorganic. All right, so identify each of these as being inorganic or organic. Has a high melting point, is inorganic. Yeah. Is not soluble in water, is typically organic. Has a formula of some carbons and hydrogens. Yeah. Formula of magnesium chloride. Yeah. Burns easily in air. Organic, right? They go for kind of a combustion reaction, and has covalent bonds. Organic as well. Yeah. Any questions on any of those there? So let's talk about hydrocarbons. Hydrocarbons is pretty much what the name sounds like, hydrocarbons. So hydrogen and carbon basically together. So the basis of organic chemistry, as I mentioned, is that carbon sort of backbone. So we want to remember our friend carbon. Carbon has how many valence electrons? Group number 4 on the periodic table. It has 4 valence electrons. Carbon will always make 4 bonds only. Let me actually write that. 4 bonds only. Yes. I say that because when people start drawing organic molecules, carbon ends up with like 42 bonds. They just keep like drawing lines. I think they think it looks more chemistry like, just keep drawing lines to the carbons. It obeys the octet rule. It has to obey the octet rule, and it will always have 4 bonds. It's also really important when to start drawing these things to keep that in mind, as we will see and talk about again. Pretty much if it is carbon and you need to get it to 4 bonds and there's no other elements involved, hydrogen is your other element. So you slap some hydrogens on there, and that's pretty much to get it to 4 bonds. So this is our simplest organic guy right here, which is methane. And if we look at this, that is 1 electron pair, 2 electron pairs, 3 electron pairs. That is 4 electron pairs. And dare I say 1, 2, 3, and 4 bonds. That is our tetrahedral geometry that's happening here. That's a 109.5 bond angle that's happening. And that is pretty much when you have single bonded carbons. That is the geometry that we see there, which is the tetrahedral geometry. Same thing here. This carbon over here is tetrahedral. So is that one as well. It has, again, 1 electron pair, 2 electron pairs, 3 electron pairs, and 4 electron pairs. They're all also bonds. Guy on the right, 1 electron pair, 2 electron pairs, 3 electron pairs, and also 4 there, with the one being shared, and also has 4 bonds. So they both actually have that tetrahedral arrangement. That is why we sometimes see, as we will see in a second, when you draw some of these are what are referred to as alkanes, they typically will have a zigzag shape because of that tetrahedral geometry. They're just each tetrahedraling out, and they typically will end up sort of in this sort of shape, this kind of zigzag shape, in terms of how they end up when they have a big chain of them together. So let's talk about some different sort of formulas that you could do. We have the space filled here, big blobs. We have the ball and stick. We have the wedge sort of form here, where the wedge is kind of coming out of the paper, the guy with the dashed line going behind the paper in three-dimensional. Most of the time here, we'll do the expanded structural formula, the condensed formula. So for example, the expanded structural formula is basically like a Lewis structure. You pretty much draw out all the hydrogens, all the bonds. That is the expanded structural formula. Pretty much you draw everything out. What is the condensed formula? The condensed formula is you don't draw out the hydrogens, essentially. You just keep them together. So you could write CH3, CH3. That would be the condensed formula. There's also a line structure formula. And line structure formula is the most basic that you could have. You basically have what I just drew on the other page, something like this. Mountain range, yes. That is an organic compound. Everywhere there is an end to the line or where lines meet, they are all carbons. So there are carbons at each of those spots. And because carbon needs to have 4 bonds and there's nothing else drawn, each of them will have the appropriate number of hydrogens. The guy at the end, there's just one line coming in, and it needs 4 bonds, which means the guy at the end will have 3 hydrogens to get the 4 bonds. The guy next to it has 2 lines coming to that carbon, which means it will have 2 hydrogens to get the 4 bonds. Same thing with this guy will have 2 hydrogens. This guy will have 2 hydrogens. This guy will have 2 hydrogens to get the 4 bonds. 2 hydrogens. Guy at the end has only 1 line coming in. We'll get 3 hydrogens there. We never ever really draw the hydrogens out. Usually with line structure, it is just a basic zigzag structure. And it's assumed that you know that where the carbons are and has the appropriate number of hydrogens. This would have, again, here 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons, and 6 carbons, again, with each one having the appropriate number of hydrogens. Any questions on that there? There's ethane, which is the second sort of organic compound there. It has 2 carbons and 6 hydrogens. And again, you can see the different sort of formulas there. So if we look at this, which is butane, and we look at the shape around each of the carbons. So if we take it this carbon here, it has 1 electron pair, 2 electron pairs, 3 electron pairs, 4 electron pairs. And again, they are each bonds. So that's 4 electron pairs, 4 bonds. That's going to be our tetrahedral arrangement. Same thing with this guy. We got 1 electron pair, 2 electron pairs, 3 electron pairs, 4 electron pairs, and they're all bonds. He will also be tetrahedral, and maybe not surprisingly enough, so will he. And the guy at the end will also be tetrahedral. So they all have basically 4 electron pairs and 4 bonds. They all have that tetrahedral geometry to it. And that is typically the geometry that you see with what are referred to as alkanes, which are single bonded carbon-carbon sort of connections that occur. We'll see that the geometry will change when you start adding double bonds or triple bonds, for example. But if you have all single bonds, you will end up with 4 electron pairs and 4 bonds. And that will give you that tetrahedral arrangement if you're talking about carbons and carbons and carbons and hydrogens. So let's officially talk about alkanes. Alkanes are really the basis of everything. So everything that we learn in organic chemistry will all come back to the alkanes. They're the basis of how you name everything, how everything is sort of comes from. Alkanes are basically have what are referred to as a functional group. And when you talk about organic molecules, different organic molecules have different what are referred to as functional groups. And a functional group is the part of the organic compound that pretty much makes it that type of organic compound. It is also pretty much, as we will see, where everything occurs. So if there's a reaction with that organic guy, it occurs pretty much at the functional group is involved. It's kind of the main part of it. Now, for alkanes, the functional group, if you consider it this, most people may not, but I'll go with it, is basically carbon-carbon single bonds. So alkanes are always carbon-carbon single bonds. That is what you know. They also have a general formula of CnH2n plus 2. So what that means is if I have one carbon, N is equal to 1. 2 times 1 is 2 plus 2 will give you 4 hydrogens. That is, as we saw, methane. If I have 2 carbons, N would equal 2 in that case. 2 times 2 is 4 plus 2 is 6 hydrogens would be involved. That is what is known as ethane. Here we have 6 carbons. 6 times 2 is 12 plus 2 is 14 hydrogens. So these are what alkanes are. They're all carbon-carbon backbone. They have the carbon hydrogens. These are also hydrocarbons because they basically have only carbons and hydrogens being bonded together. So how do we go about naming alkanes? And it's really important in alkanes. If you want to do well in organic chemistry, the faster that you learn the first 10 alkane names, the better it will be for you because pretty much everything goes back to those names. So again, really important to know the formula for those guys and the names because everything else pretty much builds off of those names and formulas. So it just helps you do that. So when we have alkanes, we have hydrocarbons that only contain carbon-carbon single bonds, carbon-hydrogen single bonds, and they are a continuous chain of carbons. When we talk about organic compounds, there are different types of organic compounds. For example, we do have just a continuous chain of carbons in a row. We could also have what is known as a branch chain, where somewhere along the way, like branches on a tree, there's some offshoots of some more carbons happening. This is what is sometimes referred to as branch chain. And we also could have sort of ring type of organic compounds, sometimes referred to as cyclo. And this is where all the carbons just sort of bond together and make basically a ring type structure. Now, the way that we go about naming it is typically when you're asked to give a name for an organic compound, we typically go with the IUPAC name. The IUPAC name stands for the International Union of Pure and Applied Chemistry. They are the 3 guys in a room that basically make up all these weird rules of how you name everything. They're the ones that come up with the names for everything and this silly rules sometimes of how you go about naming it. So typically, if you're asked to give a name in organic chemistry, that's usually the name that you want to give. Now, why I say that is because in organic chemistry, maybe more than inorganic chemistry, there's like 3 names for the same thing. There's like the IUPAC name, there's the historical name, there's the common name. So you can have the same compound that actually will have 3 different names. For example, if you have 2-propanol, that's also known as isopropyl alcohol, that's also known as rubbing alcohol. That's all the same thing, basically, right? So 3 names for the same thing. And that's very, very common in organic chemistry. Also very common in organic chemistry is they like some of these names and they've been around for a really long time. So they kind of stick with them, these kind of historical names. Sometimes it occurs. So don't be surprised if you see something that's like 3 different names for it or it's named differently sometimes. That happens really a lot in organic chemistry. But I would say most of the time, if you're asked to give a name, you want to go with a more formal name, which is the IUPAC way of naming. And for our different organic compounds, we'll talk about how to go about obviously naming each of the different sort of compounds. So with alkanes, alkanes ends in the ANE, and that is essentially how alkanes are named. They end in ANE, like methane, propane, butane, ethane. They all end ANE. That's how you know they're alkanes. We also sort of use some prefixes to help us. So here, And by the way, these line structures are off by a row. I think each of these, they go down. But these are the first 10 alkanes, and really, really you should learn these as soon as possible because it really can help you. So we'll look at it here again. They have a general formula CnH2n plus 2. So once again, if we have one carbon, we will have 4 hydrogens, and that is methane, ANE. 2 carbons, 2 times 2 is 4 plus 2 is 6 hydrogens, is ethane, ANE. 3 carbons, 3 times 2 is 6 plus 2 is 8, would be propane. 4 carbons, 4 times 2 is 8 plus 2 is 10, is butane. Once you get to about 5, if you kind of remember the prefixes we used for type 3 guys, like penta, hexa, hepta, those guys kind of come into play at this point. So if you have 5 carbons, you will have 5 times 2 is 10 plus 2 is 12. That is pentane. You have 6 carbons, 6 times 2 is 12 plus 2 more is 14. That is hexane. 7 carbons, 16 hydrogens is heptane. 8 carbons, and 8 times 2 is 16 plus 2 is 18, octane. 9 carbons, 9 times 2 is 18 plus 2 more is 20. That is nonane. And lastly, 10 carbons, 10 times 2 is 20 plus 2 more is 22, decane. As I mentioned before, pretty much that's going to be your basis for everything that we talk about. So these 10 names, I would definitely, like I said, sort of know them sooner rather than later. Also, obviously, the formulas that go with it. Here we see our molecular formula. We see our condensed structural formula. We're not drawing out the hydrogens. And these are our line structures. Again, they're each like a row off, I think, here. So these guys should go down and so forth. All right. As I mentioned before, condensed structural formula, we just really don't draw out the hydrogens. We do use the subscript next to the hydrogen to indicate how many. By the way, another thing that you sometimes will see with condensed formula is if you have a really long organic compound where like the middle part just repeats units like CH2, CH2, CH2. So for example, if we had something like this, CH3, CH2, CH2, I won't do a giant one here, but we'll do one more, maybe. There we go. Sometimes they will just go like CH3 parentheses CH2 and count up 1, 2, 3, 4, 5, put a 5, and then a CH3. So sometimes they'll kind of shorten it since it's the same unit just repeating over and over again. And that's what that means. So if you do come across that, you want to make sure you understand that that's 5 of those CH2 units in a row, and that's 5 more carbons that's basically happening. Are expanded, like I said, pretty much you're going to draw out the hydrogens like a Lewis structure, basically. By the way, we talked about carbon only having 4 bonds. Hydrogen should have how many bonds? Should only have 2 electrons, 1 bond. There should be no dots. So still, as bad as people do with carbon and load it up, they like to also here in hydrogen load it up as well. So again, don't do that. Remember, hydrogen should only look like that, right? So those are 2 very common errors people make when they start drawing these things along the way. As I mentioned before, this is line structure, and typically line structure, again, is just lines. Nothing is typically written. Even if you see a line, for example, like that, there's nothing at the end of that other than a carbon. If there was something different, it would actually be written. So again, there would be a carbon here, a carbon here, a carbon here, carbon, carbon, carbon. And once again, carbon needs 4 bonds. So the guy at the end there on the left would technically have 3 hydrogens. That's usually never drawn. The carbon here in the middle actually has 3 lines to it, which means it has just 1 hydrogen. Carbon up on top has 3 hydrogens. carbon here has 2 hydrogens. And the guy at the end will have 3 as well. So again, with line structure, if you see a lonely line, which sometimes confuses people, it is a carbon at the end of it with 3 hydrogens. That's what's known as a methyl group, as we'll talk about. If it is something else, it definitely would be drawn and written like that. That's an OH group. So if it was something other than a carbon in line structure, they will actually draw it out there and put what it is. Again, if it's just a line, nothing else written, you can assume it's a carbon with the appropriate number of hydrogens attached. Again, if it was like a double bonded oxygen, they would also draw it out like that as well. Any questions on that there? Right. So again, these are different ways you can sort of draw these things. I would say the bottom 3 are going to be the most common ones we're going to do in here. Definitely drawing the expanded structural formula, the condensed one, and line structure as well is going to be used. We probably won't do too much ball and stick modeling and molecular formula, I guess, as well. So it would be like normal as well. So here's some of those examples of all that. Now, when we look at something like butane, we have, some different ways to represent it. These are all butane. Now, sometimes when people will look at this, they will think that it is actually different things because it's drawn differently, right? So why would you draw it differently if it's not this different? And sometimes that does happen in organic chemistry. So as we'll talk about when we talk about isomers, which are really the same molecular formula but different connectivity, the way you can really tell if it is something that is sort of the same thing or a different thing is, and it's also really helpful for when we talk about how you name things, is pretty much the first thing that you look at is the longest continuous carbon chain. And what that means is you want to count up how many carbons pretty much run in a row. You could start like to the left to the right. You could start from the right to the left. You could start up on top and come down. The only thing that you can't do when you are counting up carbons to find the longest carbon chain is you can't backtrack. So if you start in one direction, you got to go until you hit a dead end. You can't like start one way, come back the other way and stuff like that. You have to kind of go one way until you hit a dead end. So you can't kind of backtrack and stuff like that. So with that being said, the reason why all these are really the same thing, even though it may look different, is if I start here left to right, that's 1 carbon, 2 carbons, 3 carbons, 4 carbons, right? If I start here left to right, 1 carbon, 2 carbons, 3 carbons, 4 carbons. If I start down here, 1 carbon, 2 carbons, 3 carbons, 4 carbons, 1 carbon, 2 carbons, 3 carbons, 4 carbons, 1, 2, 3, 4 carbons, 4 carbons straight down, 1, 2, 3, 4 carbons. They are all the same thing. They all have 4 carbons. If you count up all the hydrogens on all of them, they all have 10 hydrogens. So even though they may look different, they are actually all the same thing. And that's one way you could kind of, as we'll talk about when we get to isomers and naming and stuff like that, one way to know if you really did, for example, draw an isomer or something different is you would name them both. If you end up with the same name, you actually just drew something that's the same, even though it may look different. But if you actually end up with 2 different names, then you know for sure you ended up with 2 different sort of compounds. So given this one here, we want the molecular formula, the condensed structural formula, and the compound name. So let's take a look at this one. First off, molecular formula, we just got to count up the parts. I got 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons. So that's C5. I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens. So that would be my molecular formula, right? Just the basic of what's there, basically, right? Carbon first, hydrogen second. Condensed structural formula is basically going to look exactly like that, except I'm not going to draw out the hydrogens. So we want to break these apart in terms of like carbon units, if you will. So if we take this guy right here, that's a carbon and 3 hydrogens. That is CH3. Next, we have a carbon and 2 hydrogens. That's a CH2. Next to that is a carbon and 2 more hydrogens. That is a CH2. Next to that is a carbon and 2 more hydrogens. That is a CH2, and at the end here, a carbon with 3 hydrogens, which would look like that. That would be your condensed structural formula. Now, it's important to remember with the condensed structural formula, although the way it's written, it does sort of appear that like the hydrogen's in the middle, right, of everybody, but it's not. It's like we see in the actual picture there. The hydrogen is actually connected to the carbon, but we do write the formula that way. But it is carbon attached to carbon all the way through that thing, even when you see a condensed formula like that. So even though you see the hydrogen kind of in the middle, 2 carbons, the connection of like it is like what we see here. It is actually the carbons attached to the carbons and those hydrogens attached to that. By the way, 5 carbons, all single bonded, would be what name? 5 is pentane, yeah. The line structure for this guy would look like something like that. Yes, if I did it right, hopefully. Let's see. That is 1 carbon there, 2 carbons, 3 carbons, 4 carbons, and 5 carbons. That would be the line structure basically for it. Again, typically in line structure, you don't put the little circles like I did right there. And you don't put the hydrogens, you don't put the carbons. It's just a really basic, clean looking sort of formula. Any questions on that there? Obviously, like we can see here, this carbon at the end has 1 line coming to it. So that's why it has the 3 hydrogens. Same thing with this guy. Guy in the middle has 2 lines coming to it, which is why it has 2 hydrogens. Again, the thing you want to keep in mind is carbon needs 4 bonds, yeah? And if you run out of things to give carbon 4 bonds, give it hydrogens to get it to 4 bonds. So basically, hydrogen is what you use to get carbon basically to 4 bonds. All right, we want the condensed structural form for ethane and heptane. So once you do that, why don't you also do the line structure for could you shorthanded it? Yeah, you could if you wanted to. I would say, typically speaking, a lot of times people won't do that little shorthand unless it's a pretty good run in the middle. I would say like 6, 8, or higher, in the middle. Most of the time, people will kind of just write it out like that. It technically wouldn't be wrong if you parentheses up the middle there and did something like CH3 dash CH2 with a 3 on the bottom and that one. But I would say most people kind of save that for a pretty good amount of repeated units in a row, but it wouldn't be wrong. All right, so let's take a look at it. So ethane is our two carbons. I'll say that right. So A means that it is an alkane, and that means I know it has this general formula. And I know that it should have 2 carbons. Again, 2 times 2 is 4 plus 2, which means it should have 6 hydrogens. We're looking for the condensed formula here. So that's going to look something like this. Line structure, a little hard to draw, but it's probably the only way it would look something like that, technically speaking. You really can't do a line structure, obviously, for methane that has only 1 carbon. So this would be the best you could do there for ethane. Question on that one there. Heptane also tells us an alkane. Hepta tells us it's 7. So C7, 7 times 2 is 14, plus 2 more is a lot, 16, I guess, in that case. In this case, we can go CH3, CH3, CH2, I'm sorry, CH2. CH2, CH2, CH2. I feel like I lost count there. 1, 2, 3, 4, 5, 6, and 7 there. CH3 at the end. You also can, if you weren't sure, and you know it's 7, you could do this and just lay up 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7. And now all you have to do, if you want to figure out how many hydrogens it is, remember carbon needs how many bonds? 4. Guy on the far right has 1 line coming in, which means to get him to 4, you need 3 hydrogens, right? The guy next to it has 2 lines, which means you need 2 hydrogens. 2 lines, 2 hydrogens, 2 lines, 2 hydrogens, 2 lines, 2 hydrogens, 2 lines, 2 hydrogens. 1 line at the end means you need 3. So again, that's why it's really important to understand 4 for carbon. Yes, It helps you out when you're drawing things. It helps you out when you're looking at things. And again, pretty much hydrogen is going to be your element to get carbon to 4 if it's no other element involved. So that's going to be what you're going to use to get it to 4 if there's nothing else involved. Line structure on this guy would do 7. 1, 2, 3, 4, 5, 6, 7, I think. And it looks something like that. Yeah. And this is what I was talking about before. This is what is sometimes referred to as the zigzag shape, that kind of up and down. And that is based off of what we were talking about earlier, because each of these guys have tetrahedral geometry. They kind of get this zigzag shape when they all get together, ends up kind of going up and down. And that's why the line structure is sort of drawn like that, kind of up and down. Question on those there. Now, as I mentioned before, sometimes these alkanes and organic structures can kind of join up at the ends. So instead of like a straight chain, they kind of take the ends of them and stick them together, and they bond together. And they make these ring type structures, which are known as cycloalkanes. Cycloalkanes are much like alkanes, but they are in a ring structure. Now, one of the important things to remember in organic chemistry, in addition to the stuff we've been talking about, is pretty much the octet rule. So for example, if I had propane, which looks like this. So if I had propane and I decided that I wanted to take the ends here and I want to put them together and let them bond together. So I want to take this end and stick it together with this end, right? If I draw some weird thing like I just drew, and we call that a bond between those guys, what is the problem with that bond when I look at the carbons at the end? If those each would count as a bond, how many bonds does carbon have now on each side? It has 5. Too many. Yeah. So every time you make a bond with something that is what is known as being saturated, a saturated hydrocarbon is some hydrocarbon that has the maximum number of hydrogens. Is when you want to make a new bond, you have to get rid of hydrogens. Otherwise, you will end up with too many bonds to everybody. So every time you make a bond, say between 2 carbons, each hydrogen will lose each carbon will lose a hydrogen basically to make room for it. So when this guy comes together, we can't just stick them together like that. We actually have to get rid of a hydrogen on each one. And they will then bond in sort of a ring type structure, such as this, where now each of these carbons have not 3 at the ends, but now each of them have 2 hydrogens, right? To get each of those carbons to 4. And this is what's known as a cycloalkane. So this is propane. How we name cycloalkanes is, well, we stick cyclo in front of the name. So this guy would be cyclopropane. Yeah. Cyclopropane is the simplest cycloalkane you could have because you can't put 2 things together. Otherwise, you still have a straight line, right? So you can't put 1 thing together. So it's the simplest one that you could have. These cycloalkanes are typically drawn, line structure is typically how they roll with them. So you will see them as the triangle, also known as cyclopropane, like we just drew. You will see it as the square. How many carbons does that square have? Has 4. 4 carbons is what alkane? Methane, ethane, propane, butane. Butane, yes. And in a ring structure, this is cyclobutane. Yeah. This guy has how many carbons? It does have 5, right? 1 at each of these spots here. 5 carbons in a straight chain is pentane. In the ring chain, it is cyclopentane, right? And we can't forget our last one that we like a lot, which is this one. Has how many carbons? It is 6, even though it's badly drawn. I understand, but it's still 6. All right. So we have 6 carbons going on there. And 6 is hexane in this ring structure. It is cyclohexane. So we talked about that they have to sacrifice basically 2 hydrogens when they make these ring structures. So when you look at cycloalkanes, they actually have a general formula of CnH2n because they lost the +2 part, right? Those two hydrogens are gone, unlike alkanes that have CnH2n +2. So like our cyclopropane here has 3 carbons and only 6 hydrogens, right? 6. And that's because from the straight chain alkane, they had to give up those 2 hydrogens to allow the ends to come together and basically make that ring structure. Question on that there. So here again is our formulas, and I would say probably out of a lot of things, these are pretty typically drawn more in a line structure form. You could still do condensed, as you can see here. Blow it up, maybe. You could still do it, and it's perfectly fine. But I would say most of the time you're going to probably see these guys more of a line structure sort of organization. All right, so what is the name of this first one and the second one? So if we look at this, again, we count carbons: 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons, 6 carbons, 7 carbons, and 8 carbons. 8 carbons is octane, right? It has no double bonds, otherwise they would be drawn, by the way. By the way, we can know the formula as soon as we count that because it's an alkane. So that would be 8 times 2 is 16 plus 2 more is 18, right? So that would be the formula there. By the way, if you do have a line structure, as we will see, and there is a double bond, they would actually draw it in, just like so, yeah. Or if it had a triple bond, they would also draw it in as well. So again, if you don't see extra lines, then you could assume that they're all single bonded as well. This is guy we just did there. That's 1, 2, 3, 4, 5. That's based off of pentane. It is in a ring structure, so that's going to be our cyclopentane. And again, because we know it's a cycloalkane, it should have that form of CnH2 times N, which means C5H10 in this case, right? Would be our formula. Again, knowing that versus this guy, which is our straight chain alkane, which has this as its general formula. Any questions on that? Well, that was a wonderful intro to organicness.